Hello and welcome back to a new taste of physics. Today I want to talk about my latest research work published this summer in the scientific journal Optics Letters. Let's get into science. When we study something from a quantum point of view, at the scale of elementary particles, the laws of nature are somewhat different from those we find in our day-to-day life. Photons, for example, the particles of light, they have different properties when it comes to individual photons from when we talk about light beams, electromagnetic waves. For example, if we send a beam of light to a beam splitter, 50% will follow a straight line and 50% will bounce. If we send a single photon, the same thing happens. We do not know from which port it will leave, but we know that 50% of the times it will leave from each other port. If we send two photons, one to each input channel, we hope to have four possible answers, that both leave port C, both leave port D, the one that came from port A leaves from port C, while the other one leaves the other way, and vice versa. This is what we would expect from a classical point of view. But if the photons are identical, indistinguishable from a quantum point of view, we find that the photons always leave the beam splitter in pairs. So the last two options do not occur, they are forbidden. This is how the photons interfere. They actually have a wave behavior as far as photons are identical. If the photons are indistinguishable, then we recover classical result. If they are distinguishable. In many techniques and experiments in optics, it is very important to ensure that the two photons are identical. In my last research work, in collaboration with researchers from Duke University and Ohio State University, we showed a way to extract quantum information from a single photon by doing experiments with several photons, with classical light, with laser. The laser is a very interesting and versatile instrument. We have very diverse types, powers, and wavelengths. We can send continuous light or pulses of light. If we send pulses and attenuate the intensity, we can arrive at the situation where we have, on average, one single photon per pulse. But it turns out that for laser light, we can't guarantee that there is a photon in each pulse. We can guarantee, though, that on average there will be a photon per pulse. We will have empty pulses, and pulses with two photons, and some with three photons. Unfortunately, we don't have off-the-shelf, agile and easy to control single photon sources on demand. This is a big problem. For example, if we want to send encrypted information through the polarization of the photons, if we don't know if there is one photon or two in our pulse, a spy could place a beam splitter and steal one of the photons without us finding out. In our experiment, I used pulses of light from a laser. Pulses of light were then attenuated with a filter until I had only one photon in each pulse on average. The pulses of photons were sent to the two input ports of a 50-50 beam splitter. Then I recorded the photons that came out of the beam splitter. Sometimes I had a click on detector A, other times click on detector B, and some very few times coincidence clicks. These detectors only give clicks, regardless of whether one or more photons hit. There is no way to discern the number of photons that hit the detector. But in many experiments, we can only consider events which there has only been a single photon participating. With a simple mathematical development, we have found a way to extract information that corresponds to only those single photon events, from one photon interaction. That is, only one photon entering each input port of the beam splitter. And we can discard those that came from multi-photon pulses, those events that bring pulses with several photons. We found a way to focus only on those that are clean pulses. To check this, I sent pulses of identical photons to both input ports of the beam splitter. With the photons being identical, I didn't find any coincidences behind the beam splitter. Both photons left the beam splitter in pairs as predicted by quantum mechanics. Then I changed slightly the time of arrival of one of the pulses with respect to the other. This made them slightly distinguishable, and then I began to detect coincidences, which increased as the difference between the photons increased. This effect is called the HONG-OU-MANDEL effect, in honor to the scientist who studied it for the first time in 1987. And this plot is the HONG-OU-MANDEL dip. From this graph, with our method, we have been able to extract information that comes only from the one photon interaction, and discard the non-useful multiple photon pulses. One application of this is if we have only sent encrypted information messages to Bob using photons to create a quantum key. If a spy wants to tamper up the pulses on the way to Bob, she would slightly disturb the pulses. These perturbance will make them distinguishable and would deteriorate the HONG-OU-MANDEL dip, revealing the presence of pirates. If you want to read the article, you can go to my website and read it, or if you have questions or that, I will be happy to answer you. And may the science be with you.